Welcome to this presentation on the stiffness matrix. In this presentation, I'm going to focus on transformation of the stiffness matrix. So right here, we're looking at is the stiffness matrix in local coordinates, local coordinate system, and element form. And that's what we're going to look at and seeing how we can get this to change and get it to our global coordinate system and our system form. So let's zoom out a little bit here to start. You can see what I have here. So I have an element up top here. And if we look at this element a little bit more closely, we're going to have two nodes that make up this element. So I got a node down here, and I put a node up here. And so the coordinate system for this initially starts out with, we got, it's kind of a big line right there. Let's go back to a different line here. Okay, so we got the x component is along our element, and the y component comes out here. And this is both at node I. And then we have the coordinate system up here at node j. And we have the x component of that going this way, and the y component coming out this way. So again, the x component here is along, axially along our member here. All right, good. So let's zoom out here and look at our stiffness matrix. Where does this stiffness matrix come from? Trying to understand what it is and where we want to take it, we need to know where it came from. So over here to the side, I'm going to put in our equation here. This came from the stiffness matrix, looking at the force being applied at each node. So the force at node I is equal to our stiffness of our member. And then we have the local displacement at node I in the x direction minus the local displacement at node j in the x direction. And likewise, for the force at node j, we have the stiffness times the local displacement at node j in the x direction minus the local displacement at I in the x direction. So those two guys feed in to what we're going to find in the stiffness matrix. Now, the stiffness matrix is going to be composed of just our k values, here and here, and how they multiply into the displacement. So let's see how that works here. And this is presented in the other presentation. I'm just kind of do it more drawing it in here. So let me zoom in. So the actual form of this is k 0 minus k 0. And the second row is all zeros. And then we have minus k 0, k 0, 0, 0, 0, 0. All right, so let's zoom out here and see why that is. If we look at our equations again here on the left-hand side, we see that our u's here is the u. This is the at the node I in the x direction, and so if we draw these in on our matrix over here, so zoom back in, and we put these in. These would be the local coordinates. So I'm going to use the colors purple, lavender for local. And so we have I component in the x direction. We have the I component in the y direction. We have the j component in the x direction, the j component in the y direction. So we can represent these columns with these particular indices. And if we look across the rows, we can look at these as the displacement at node I in the x direction, the displacement at node I in the y direction, the displacement at node j in the x direction, and the displacement at node j in the y direction. Now these values are here, they're just symbolic. The colored ones they aren't actually there in any of the matrix math that we do, so just be aware of that. So if we would take this first row and we'd multiply it by the purple U's, the lavender U's we have on the right-hand side, you'd see that we'd have k times U, so k would multiply into U Ix, and so if we zoom out here again, you can see that here is k Ux, and then we have minus k, and we multiply by Ujx, and we get minus U, the displacement at node j in the x direction. And likewise, we're going to see that here for the force at node j, we have k Ujx minus UIX, so we get a minus for the K here and a positive for the K here. So that's where they come from. There's no force in the Y direction, that's why we have 0 in the second row and zeros in the fourth row. Alright, so coming back over here to look at this, let's look at focus on the coordinate system and the form here. So the coordinate system we're dealing with is, as I mentioned several times now, it's the local coordinate system. And the form we're looking at here is the element form. We're dealing with an element. We haven't kind of zoomed out to the whole system. So this is on the elemental form. All right, so that's what we have here. That's all the local coordinate system, element form. That's what we got. So how do we get from this over to here? All right, so how do we get to this guy over here? This is the question mark. How do we do this right here? How do we get to that stiffness matrix? Somehow we have to transform ourselves into this new form. And that takes the transformation matrix. So let's looking at that a little bit. So we'll zoom in here. What is happening in this middle section? Well, first of all, let's look at how we can get here. So we have our little element here. I'm going to hand draw it this time. We got node I here, and we got node J out here. And then we're going to transform from, and what we're doing here is coordinate system transfer. So we're transforming from local to the global coordinate system. So we got to tell it where it's at in space. So the way we do that is we do it by the angle of our member, and the angle is based on horizontal out from node I, and we go up, compare that to what we have actually along our member. And I'm going to change colors here, go to red, and so we look at this angle here, and that angle is our theta. So we have to go from horizontal over to where we have the kind of a center line along our member. And we do the pivot point. The pivot point has to be at node I. That has to be our pivot point. So whenever we number our nodes and create our elements, it's very important that we note what is I, what node is node I, and what node is node J, because that defines what the theta is. And it'll be in the next step, the next transformation that we have to do. All right, so in this transformation overall, what we're doing is we're trying to create this capital K matrix, and we're doing it by taking a transformation matrix, multiplying it times our element local stiffness matrix, and then we take the inverse of our transformation matrix. All right, so this transformation matrix is, so we'll say where, and move over here. So that transformation matrix is this guy. So we got cosine, we got cosine and sine, and we get 0, 0. Oops, let me get those a little bit further apart there. 0, 0. And then we're going to have minus sine, cosine, 0, 0. And then the rest of it you just have to see with the other presentation. You get the idea what's going on here. So I didn't put the thetas in here because I wanted to highlight those in their own color, right? Because those thetas come from up above. So we got to make sure hopefully color-wise, you can track where things are coming from here. And so those come from that theta definition of this, the angle to the member there. All right, so we did our transformation. We now have our K value, so let's look at what that K value is. So we're moving over here. All right, so what do we end up with after we do the transformation? All right, we have this global K, and it turns out we have, and let's zoom in a little bit more here so I have plenty of space to write this in here. All right, we come up with cosine, let me change back my colors here. We got cosine squared. So I'm not going to put the theta there because that's, again, I want to put it in red so we have the same color code for the angle there. So sine cosine minus cosine squared minus sine theta cosine. And the next time we're going to have sine, cosine, we'll have sine squared, and etc., etc. So again, this is a 4 by 4. Always is a 4 by 4 for these types of elements. So we got theta there, theta, theta. We're going to do theta here, theta, theta, cosine and sine. All right. So after we do this process here, right, after we do this, we end up with what I just wrote up here. All right, so that is our stiffness matrix now. Our stiffness matrix we are now in global coordinates. And the form, though, is still the element form. All right, so let's look at the meaning of this a little bit more. So zooming in here. So the meaning is we got node I in the x direction. Here's node I in the y direction. Node j in the x direction and node j in the y direction. So that's essentially what we have there, very generically for this case. But we're in global coordinate system now. So if we look at our at the right-hand side, looking at that as the representation for the coordinate system, we have u's now, capital U's. So we're looking at this capital displacements. All right, and this is u, displacement at node I in the x direction, displacement at node I in the y direction, node j in the x direction, and node j in the y direction. All right, so we went from local displacements to global displacements doing this transformation. And now if we slide up to the top, we can see how that affects our element. Our element now becomes, here's node I, so we got the x, so capital X there for that coordinate, and y for this coordinate, add node I, and up here at j, we're going to have x and y. Oop, do capital Y there. All right, so capital Y. All right, so zooming out here, let's look at our overall work so far. Let's zoom in here, so there we go. All right, so we have our local stiffness matrix and our global stiffness matrix, both in element form. And we shifted from our local coordinate system, so we can see how the x is along the axis of our member, to global coordinate systems where our x and y are based on the global coordinate system, hence the name. All right, and we had this this transformation that occurred in the middle to figure out, we used it to figure out our theta, so we could transfer and do that shift from the local to the global. All right, so now we need to bring things together. We have, we're in global coordinates, that's good, but we're still in element form. We still have just our individual elements, and we might, we probably have other members if we're connected to other things. So how do we connect into those pieces? So we need to do another transformation. So let's look at where we're going here. All right, we want to make it from our global matrix here into our global. And actually, let me just write it in here. So we'll zoom in here. Our coordinate system is obviously going to be a global coordinate system here. But the form is going to be the system form, because we need to integrate with other pieces. So looking up top here, what we might have as an example is we could have a member here, and they actually share nodes, and then we might have another member that goes across like this, and they share this node. But we have this third node out here. We have this third node out here that this member doesn't use at all, and we have to somehow prepare this guy so that he'll pick that value up. Oop, sorry, I was trying to get rid of that stray mark down below here. Let's see if I can erase it. No, all right, well, it might just be there. All right, and say we have some boundary condition 2 here. We'll put a pen here. All right. So let's figure out how we're going to get there. So if we move back over here, how do we make this shift from, well, we have the global, we're in our global coordinate system, we've got to go from the element to the system form. All right, so that's where we're going to use these. I think I've given them similar names of the transformation matrix, but basically we're going to, in the MathCAD file, I call it the trans matrix, so maybe we'll kind of focus on that terminology. So the overall trans matrix. And so if we have the K in the global form, that's going to be equal to our trans matrix and the transformation of it, at least how we have it set up. So it's going to be, at least our MathCAD, we have some number here for whatever element we're on. We have our global coordinate system, but element form of our stiffness matrix, and then we multiply it times our trans matrix. Okay, so what is this trans matrix? So what we got here is with 3 nodes, if we have 3 nodes in our overall system here, 1, 2, 3, we need to go from our 2 by 2, so we're always going to have a 2 by 2 here. In this case, it's always going to be a 2 by 2 for trusses. And we need to go from a 2 by 2 to a, so 1, 2, 3, 4, and then we're going to need 5, 6 for this guy over here. So we need to go from a 4 by 4 to a 6 by 6. So how do we make that? And that's what these transformation matrices are for. So zooming in here, let's look at that a little bit more closely. So I'll say where we got trans number is equal to our 6 by 4. And so if we look at the first column, that's going to be our node I, the x component, the node I and the y component, node j x component, node j y component. And then down the right hand side, these are going to be our global coordinates, so u 1x, so now we're actually going to be labeling the nodes that we have, 1y, u2x, u2y, u dot 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 along the way, the rest of the way down. All right, so we don't have 2 more, but I want to keep this fairly generic here. All right, so then what do we put in here? What do we put in this matrix? So we got to be careful there. And so what we're going to do is we're going to put in wherever node 1 is, or node I is, we're going to do 1, 0, 0, 0, 0, 1, 0, 0. So let me put some additional text in for that. So this part here, we're going to say put in the rows of node I. All right? So whatever node I is for your element, everything that's happening in this circle goes in that row. So if node I is node 1, this row goes in the global displacement 1x, and if and this one follows in the next one in 1y. If node I of your element is node 3, then after 2, if this is 3, then these 2 rows go here and here. All right, so it's all about what node I is in your element. That's where these 2 rows go. All right, likewise, if we have, for node J is going to be 0, 0, 1, 0, followed by 0, 0, 0, 1. And both these guys put in rows of node J. All right? So again, if node J is node 2 in your element, then this row would go right across from the displacement of node 2 in the x, and this one would be the next row that follows for row 2 in the y. All right, so simple as that. So you find your node I, find that row, put 1, 1, and then for node 2 you find that one and you put 1, 1. All right, so hopefully that makes a little bit more sense there. And just to know, everything else is 0, so maybe just I'll highlight that real quick here. So all other rows are 0. All right, so let's zoom out here, see what we got here. All right, so now that we're at our system form, global coordinates. What do we got here? All right, so we're definitely in global coordinate systems. So you got u1x, so you got u1y, u2x, u2y, u dot dot dot. All right, just like we had in the transformation mix side here. And we can represent the top similar way, u1x, that doesn't look like a lowercase, u1y, u2x, u2y, u, etc. All right, so this one I'm not going to put any values in because I don't want to, it changes based on each element that you may have. So let me write this. This is going to be a square matrix, must be a square matrix, and it has with dimensions of it's going to be the total number of nodes times 2. Right? So the total number of nodes times 2. And the reason for 2 is because x and y components. Right, so if we only had one member, strangely enough, if we only had one member, we would have node 1 and node 2, and then we'd have x and y for each. So total number of nodes would be 2. 2 times 2 is 4, so 1, 2, 3, 4. And that's how that works. All right, but the way we get this for any element is we have to do this process. Whoa, sorry about that. This process first, right? Because this process will get us this for one element, right? We'll get it in global coordinate form for one element, and then we'll have to add these guys up to get the global stiffness matrix for our whole truss system. All right, so I hope that was valuable going through that process. I will print this to PDF, so this will be accessible in the link notes. But yeah, feel free to ask me any questions, leave those in the comments, and I hope this was helpful. Thanks.